Okay, think about this for a second. You're sharing, say, an important work doc or maybe just a personal photo album online. You automatically think, right, who gets to see this? Who can maybe edit it? And definitely who can't see it? Seems pretty intuitive, doesn't it, on that personal scale? But what happens when you blow that up? Like to a huge company, a global one maybe, or even, government secrets. How do you possibly control who sees what then? Well, today we're doing a deep dive into exactly that, the really fascinating world of access control and security models. And these aren't just like abstract ideas, they're the actual blueprints, the architecture for how information gets protected. They decide who sees what and exactly under what conditions. Now, you've given us a great set of sources here. They lay out the core ideas, specific models, a lot of stuff you'd see if you were studying for, say, CISSP. So our mission today, let's unpack all of this, pull out the key bits of knowledge, and try to make even the really detailed models clear, engaging, and, well, useful for you. Think of it like a shortcut, maybe, to really getting the logic behind digital security. And understanding these models, it's not just for security pros. It really helps you grasp the logic behind, well, almost any system that manages permissions, from your own computer right up to the most secure data centers. It gives you those aha moments,
Okay.
about why systems are built the way they are. Okay, let's get into it. Our sources outline several broad categories of access control. Let's start with probably the most common one, the one that feels most intuitive for a lot of us, discretionary access control, or DAC. The core idea here is pretty simple. The owner of a resource decides who gets access and how. It's discretionary because, well, the owner has the discretion, the choice.
Right. And you see this all the time in operating systems like Windows or Unix. If you've ever used chmod on a file to set read-write permissions, that's DAC in action.
Exactly. And one source put it perfectly. Think of a photo album where you choose which friends can see each photo. You control the sharing rules. No central policy forces it. You're the boss of your photos.
Which is great for flexibility for individuals managing their own stuff. But the downside, it can become chaotic in large orgs. That's what the sources say.
Yeah, because permissions end up scattered everywhere. It gets really hard to track who has access to what.
And there's a key security weakness they point out, too. DIG is vulnerable to things like Trojan horses or viruses. Basically, a trusted app you run might get tricked into passing its permissions onto something malicious.
Oh, right. That's a subtle but really important risk. For a quick way to remember it, maybe think DIA is adult's choice. The dad, the owner, decides who gets into the castle, the resource.
Simple enough. But that very simplicity, that individual control, is exactly what doesn't work when the stakes are super high.
Right, like with government secrets or critical infrastructure, you can't just leave that up to individual choice. Which brings us to almost the complete opposite. Mandatory access control, or MC.
Okay, so with MSC, the system makes the call, not the users. Access is based on centrally managed labels. Think clearances and classifications.
Yeah, so users and data objects, they both get fixed labels, like top secret, secret, confidential, that sort of thing. And a user can only access an object if their clearance level dominates, basically, is equal to or higher than the object's classification.
And crucially, users cannot change these permissions. It's fixed by the system, administrator, or policy.
The sources also highlight that MSC essentially uses a lattice structure. We'll come back to lattices, but it's because these labels are hierarchical.
Right, layers of security. And the real-world example they give is great. A military intelligence facility. Everyone in every file has a classification, like a colored badge. You need the right badge color, the right clearance to open the corresponding file.
Yeah, no getting access just because you know someone. It's strictly your clearance versus the file's label. So the mnemonic could be MSE equals machine controls, like a strict robot guard checking your badge.
And that's exactly why it's the standard for high-security environments. It removes that risky individual discretion, which raises a key point, connecting this to the bigger picture. How does this rigid structure help prevent information from flowing downwards? That's vital for confidentiality, right? Making sure secrets don't leak to lower levels.
Absolutely. It's designed for that strict top-down control. Okay, moving on from MC, let's talk about role-based access control, or RBAC. This is probably the model most people listening will encounter in like a typical company.
Definitely. It's huge in the enterprise world.
So with RBAC, access isn't tied directly to individuals. It's tied to roles.
The organization defines roles first: manager, accountant, HR, system admin, whatever makes sense. Then permissions are assigned to those roles.
And users, they just inherit permissions by being put into one or more roles. It centralizes control really effectively.
The analogy in the sources is good. Picture a company where jobs come with keys on different keychains. A finance keychain opens budget reports. An IT keychain opens server rooms.
New hires pick up the keychain for their job role. No need to program each lock individually for each person. Makes perfect sense.
And a major benefit is tackling what's called privilege explosion. Instead of managing permissions for hundreds of users, you manage them for maybe a dozen roles.
Much simpler. And the sources note it can coexist with MAC or D-Day, so it's flexible in that way too.
For mnemonic, maybe RBAC rules by all circles, grouping people into circles or roles.
I like that. Okay, so RBAC organizes by job function, but what if access needs to depend on something else, like when or where you're accessing from? That brings us to rule-based access control, or RBAC. This adds a layer of dynamic decision-making.
Right. RBAC decisions are based on predefined rules or conditions. Often they're environment-based.
It's more dynamic, like simple if-then logic. It checks conditions like time of day, location, or security context.
The sources give clear examples. A trading system only allowing trades during market hours. That's a time-based rule.
Or a firewall blocking logins outside business hours, or maybe from certain IP addresses. Those are rule-based access control lists, ACLs.
So the mnemonic could be, RBAC goes rules unchecked by attributes or roles, because it focuses purely on the conditions.
And that dynamic aspect you mentioned is key, isn't it?
Absolutely. If we connect this to the bigger picture, RBAC is essential for things like break glass policies, where you grant emergency access under very specific logged conditions, or just systems that behave differently after hours. It's about adding that contextual intelligence to access decisions, making them smarter.
Okay, contextual intelligence. That leads nicely into the next one, which takes that idea even further. Attribute-based access control, or ABA. This is where things get really fine-grained and, honestly, quite powerful.
Yeah, ABAC is seen as very advanced, very flexible.
Access here is granted based on multiple attributes, not just one thing like a role or a simple rule. It considers attributes of the user like their department, their clearance, maybe their current location.
And attributes of the resource like its classification level, who owns it, what project it belongs to.
And even attributes of the environment or context, time of day, the current threat level, the type of network being used.
Policies then combine these attributes using complex logic.
So the sources say it's very flexible and powerful, but the downside, it can become complex, which makes sense.
A good example they give. An employee can access a file only if their department attribute matches the file's department label, and their location attribute is in the office,
Yeah.
and the time attribute is business hours.
Right. Or maybe a system only lets someone approve a purchase order if they have the manager attribute and the full-time attribute and the budget authority $1,000 attribute.
Lots of factors. So the mnemonic works well. ABAC, all relevant attributes checked. It's like a multi-factor test for every access request.
And a key insight from the sources. ABC can technically express anything RBAC can, because a role can just be one attribute among many. But RBAC can't necessarily express all the fine-grained stuff ABAC can do.
That's a really important point about its power.
Okay, now we mentioned this concept briefly when we talked about ME, the lattice-based model. Let's give that its own moment.
Yeah, because it's fundamental to understanding some of the most classic security models.
So a lattice model basically organizes users and data into hierarchical layers, think levels, and it enforces really strict rules about how information can flow between those layers.
Every user and every object gets a security label again, like top secret, secret, confidential, unclassified.
The analogies help here. Think of it as stacked floors in a building. You can only move information up or down between floors according to fixed rules.
Or picture a ladder, the lattice itself. You can only climb up and down according to the rules.
It's all about structuring and controlling that information flow rigorously.
And this idea of layered security and controlled flow, it's absolutely fundamental, as you said. It underpins how we think about confidentiality and integrity. The whole concept that information generally moves in only one direction, either up or down the lattice, depending on the goal, is critical.
And the two classic models built right on this lattice idea are Bell-LaPadula for confidentiality.
And the BIBA model for integrity.
Perfect. So now that we have those broad approaches, DTE, MAC, RBAC, RBAC, ABAs, and the lattice concept, let's zoom in on some specific, really foundational security models, starting with the one that's all about secrets. The Bell-LaPadula model, or BLP.
Right. If you want to keep information confidential, BLP is the historical heavyweight.
Its purpose is solely confidentiality. As one source puts it, it is solely about keeping secrets. Full stop.
And it achieves this through two core rules, which are quite elegant, really.
First, the simple security property, nicknamed no read-up.
Meaning a subject like a user at a lower security level cannot read data classified at a higher level.
Yeah.
Simple.
Second, and this is often the key one, the security property, pronounced star security property, nicknamed no write-down.
This means a subject cannot write information from a higher security level to a lower security level.
So you can't accidentally or deliberately leak top-secret info into a secret document.
The combined result: information can only flow upwards in classification. Secrets stay secret by not being allowed to move down.
The analogy provided is helpful. Picture a government library with restricted sections. A confidential level agent can read confidential and unclassified documents. Reading down is okay, but cannot read secret or top secret books. That's the no read up rule.
And if they write reports, they can mark them confidential or higher. Writing up is okay, but they can't declassify a document from confidential down to unclassified. That's the crucial no write down.
Got it. Mnemonics. Maybe bell rings high, secrets lie low. Or just write up, read down, W.
The sources also mention a nuance, a stricter version called the strong star property, which basically means you can only read and write at your own level. No reading down or writing up allowed either. Even stricter.
Interesting. Okay, so BLP is the king of confidentiality. What about the flip side? Keeping data pure and trustworthy. That takes us to the BIBA model.
Exactly. If BLP is about keeping secrets, BIBA is about keeping information accurate and uncorrupted. It's an integrity model.
And the sources say it's essentially the inverse of Bell LaPadula, which makes sense, given the goals.
It also has two main rules, mirroring BLP, but for integrity.
First, the simple integrity property. No read from lower integrity.
So a subject at a high integrity level, like trusted system code, shouldn't read data from a lower integrity level, like potentially dodgy user input, prevents contamination.
Second, the integrity property, no right to higher integrity.
Meaning a subject at a lower integrity level cannot write data to a higher integrity level, prevents less trustworthy sources from corrupting more trustworthy data.
So the result is preventing contamination of high integrity data. You can only write at or below your integrity level, and only read at or above your level.
The analogy here is the military chain of command again, but viewed for integrity. A private, low integrity, can receive and read orders from a general, high integrity, that's reading up, which is fine for integrity.
But the private should never issue orders to the general. That would be writing up, violating integrity.
The mnemonic could be BIBA, book integrity, and maybe you remember no low reads or high deeds.
Okay, that contrast between BLP and BIBA confidentiality versus integrity is really stark.
And it raises that important question. Why is integrity just as critical as confidentiality? BIBA is designed to guard against, sloppy mistakes or malicious edits. It ensures that critical data remains trustworthy, which is absolutely vital for any system where accuracy is paramount. Think financial systems, medical records, industrial controls.
Good point. Okay, next model. Clark Wilson. This one feels a bit more grounded in business processes.
It definitely is. It's described as a commercial integrity model, focused on preventing fraud and errors in, day-to-day business transactions.
It's built around well-formed transactions and separation of duties. Those are the key concepts.
So core features. First, well-formed transactions. Data can only be changed by specific, pre-approved, certified programs, which they call transformation procedures, or TPs.
Users must use these approved programs. No direct access to fiddle with the data.
Second, a big one, separation of duty.
What?
No single person should be able to both certify and execute a transaction. You need multiple people involved for checks and balances.
And third, it uses what's called an access triple. It maintains a link. Subject, program, object.
Which means the subject user doesn't talk directly to the object, data. They have to go through the approved program, TP.
The bank analogy in the sources works well here. Imagine withdrawing money involves two clerks and a special form. You can only withdraw cash by filling the proper form. That's the well-formed transaction.
And having it authorized by a manager, separation of duties.
Using the bank's official system, you can't just, reach into the database yourself.
It must go through the approved teller software, the transformation procedure.
Makes sense. For a mnemonic, Clark Wilson keeps data clear. Or maybe CW, EC hacked, W workflows.
What really stands out with Clark Wilson is that emphasis on controlled processes. It's a great insight. It recognizes that integrity isn't just about stopping bad guys from getting in, it's also about stopping authorized users from doing unauthorized things or making mistakes by enforcing strict workflows.
Very practical. Okay, next up is a model designed for a very specific, sometimes tricky situation. Brewer-Nash, also known as the Chinese wall model.
Ah, yes, the conflict of interest model.
Exactly. Its purpose is to prevent conflicts of interest. It does this by dynamically restricting access based on what a user has already seen.
How it works is pretty neat. Once a user accesses data related to, say, company X, a metaphorical wall goes up, blocking them from accessing data related to company Y if Y is a competitor of X.
And it's dynamic because the access permissions change based on the user's previous actions. What you can see depends on what you've already seen.
You see this often in finance, consulting, law firms, places where professionals handle sensitive information for competing clients.
The analogy captures it. Picture a consultant working with multiple competing companies. If she reviews Project A for Company X, she then can no longer see any Project B for Company Y, a competitor.
There's an invisible Chinese wall once you pick a side for a particular dataset type. You can't peek over to the other side for competitors in that same type.
Our mnemonic is pretty direct. Brewer builds a Chinese wall, or maybe break no alley's secret if you want something more conceptual.
It's a great example of how access control has to consider not just security levels, but also business ethics and confidentiality agreements.
Definitely. Okay, let's shift gears slightly. The next few models are less about policy, like confidentiality or integrity, and more about managing rights and analyzing system safety. First, the Graham-Denning model.
This one focuses on how you actually manage subjects, objects, and the rights connecting them. It tries to formalize the administration of permissions.
Right. Its core is specifying 8 primitive operations for safely creating and deleting subjects, users, and object, files, resources, and for granting or revoking rights between them.
These operations are things like create subject, create object, delete object, read access right, grant access right, delete access right, and transfer access right.
The analogy of a security administrator at a data center works. Adding a new server, object, create object, adding a user subject, create subject, giving access, grant right.
Or like librarians controlling who can check out, read, add, grant, or remove books.
So the mnemonic Graham and Denning manage grant rights fits pretty well. It's about the fundamental actions of rights management.
Laying down the basic rules for secure administration.
Building on that, we have the Harrison-Russo-Ullman, or HRU, model. This one gets a bit more theoretical.
Yeah, HRU takes Graham-Denning's administrative focus and asks a deeper question. Can we prove if a system's state of permissions is actually safe?
Its purpose is to expand on Graham-Denning, focusing on the integrity of access rights themselves, and figuring out if granting a new right could potentially lead to an unsafe state down the road.
It introduces a formal state machine model. Think of the system's current permissions as a state, and it provides algorithms to check if a state is safe. Meaning, can a subject ever gain a right they shouldn't have, starting from this state?
So it tackles complex questions like, if I let Alice grant Bob this specific right now, could that somehow, through a series of future allowed actions, let Bob eventually get access to Charlie's private files?
The analogy is like a simulation machine. It checks. If I let Alice give Bob a new right, could Bob ultimately get access to Charlie's files? HRU acts like a supervisor saying safe or unsafe about the current configuration.
So mnemonic. HRU, how rights unfold. Trying to predict the consequences.
And this brings up the critical safety problem in computer security. It's not enough to set initial permissions correctly. You have to ensure that the allowed ways permissions can change or propagate through the system don't accidentally create security holes over time. HRU provides a formal way to analyze that risk.
Very important for building provably secure systems. Okay, next is the take-grant model. This one sounds more active.
It is, and it's often visualized using graphs. It's a model for analyzing how rights can flow, rather than a policy itself.
Right. Its purpose is a graph-based model for analyzing how rights can flow between subjects and objects, a tool for security analysis.
Its core is defining 4 rules: take, grant, create, and remove. These rules dictate how subjects can acquire rights from objects or other subjects, or give rights away.
And you use these rules on the graph model to figure out if a subject can, through some sequence of take and grant operations, eventually acquire a certain right they don't currently possess.
The classroom analogy helps. Picture students passing permission slips. One student can grant permission to another, grant rule.
Or take a left-behind permission slip from someone else, take rule.
Over time, who holds the permission slip can change. The take-grant model tracks all those passes and grabs to see who could end up with the slip, meaning the access right.
Simple mnemonic. Take some, grant some. It's all about those two key actions.
So it's less about setting policy and more about analyzing the potential consequences of the policies you've set, specifically around privilege escalation.
Makes sense. Diagnostic tool.
Oh.
Okay, one last model to cover, and it's a bit of an ideal maybe. The non-interference model.
Ah, yes. This is considered a very high assurance model, often more theoretical, but incredibly important conceptually.
Its purpose is described as a high-assurance confidentiality model, serving as a theoretical benchmark, the gold standard, perhaps.
The core idea is powerful. Actions at a high security level must have no effect whatsoever on what happens at a lower level.
It means a low-level user shouldn't even be able to notice or infer anything about what a high-level user is doing, not even indirectly.
The result is absolute non-interference from high to low. It prevents even subtle information leaks, like noticing system load changes or timing differences caused by high-level activity.
The analogy of parallel universes, quite evocative. Think of two parallel universes, high-level and low-level. What happens in the high-security universe doesn't ripple into the low-security universe at all.
A low-level user lives in an isolated world where high-level events are completely invisible, like they don't even exist.
Mnemonic. Non-interference. No info. No noise. Absolutely no signal leakage.
And what's fascinating, connecting this back, is that while achieving pure non-interference in complex real-world systems is incredibly difficult, maybe even impossible sometimes, it gives us an ideal to strive for. It forces security designers to think about the most subtle, covert channels through which information might leak. It really underscores the extreme lengths needed to protect the most sensitive information, ensuring not even a whisper, not even a timing fluctuation, betrays high-level activity to lower levels.
Wow. Okay, that was quite a journey through the foundations of access control. We went from something as simple as sharing a photo album with a friend,
All the way to managing top-secret government data with MAC and BLP,
preventing conflicts of interest with the Chinese wall model.
and even analyzing the theoretical safety of permission changes with HRU and take grant.
It really covers a huge range.
It does. And if you connect it all to the bigger picture, you can really see how each model tackles a different facet of this incredibly complex problem, securing information. They provide a structured, logical way to think about it, a common language for building robust security architectures.
Absolutely. And understanding these models, it really helps you see beyond just, passwords and firewalls. You start to understand the underlying logic, the design philosophy behind how digital security is actually built and enforced.
Recognizing the method behind the madness, so to speak.
Exactly. So thinking about the future, information is just exploding, right?
Right.
And how we access it is becoming so much more dynamic, interconnected. Which of these models, or maybe combinations of them, do you think will be most critical going forward to balance both security and usability?
That's a great question. And maybe tied to that, how do real-world systems actually manage this balancing act today? Juggling the confidentiality needs, like from Bella Padula with the integrity needs of BIBA, and still trying to get the flexibility of something like ABAC, all at the same time. How do they
Yeah.
make that work in practice?